Okay, very good morning to all of you. So in the last class, what we learned was a little bit about static latches and static CMOS registers. Today we are going to I'm going to introduce you to a new concept which is known as dynamic registers. Okay. So, as in the static CMOS, there are a few drawbacks which we'll again revisit. One is a large area. That means if you see this is a simple SR latch, it requires around 8 transistors, right? And also, if you remember from the last class, the sizing of these clock and S and R NMOS have to be large enough to overcome the resistance provided by M2 and M4 in building up this potential. They'll try and keep the potential at 1, while these transistors have to bring down the potential to 0, the node voltages out here to 0. So they have to overcome the current which is provided by M2 and M4. So accordingly these have to be sized up, right? So all these result in a large area, complexity, static dissipation. Obviously there are paths between VDD and ground through the off transistors, but there, if you see here, multiple paths are available here, right? So you will find static dissipation is high. Dynamic dissipation, again short circuit loss, switching loss, all these which are commonly this is a drawback of any static circuit. So that is the same drawbacks are there in a static CMOS latch or a static CMOS register. Okay, so we have something known as an dynamic register. Okay, in the dynamic register, the principle of operation is temporary storage of a charge on a parasitic capacitor. Okay, so there is no latch which permanently stores 0 or 1. It is on the gate of an inverter, whatever parasitic gate capacitance is there. So we are going to feed some 0 or 1 there, and then give and the input line becomes an high impedance line. But whereas there is no path available for the charge to get discharged. Okay, so it can hold that charge, but over a period of time that will through the off resistances it is going to get discharged. So it is only temporary storage. Okay, so that is it. So storage and hence can be kept for a limited amount of time, typically in the range of milliseconds. Actually milliseconds, it appears to be very small, but then for today's processors which operates in gigahertz, milliseconds is a pretty long duration. Milliseconds corresponds to few kilohertz, right? So even if it is holding for few milliseconds, it is pretty useful for us, right? Now, to preserve signal integrity, a periodic refresh of its value is required. So in case we need to store a data in milliseconds for some reasons, still we can use dynamic registers through periodic refresh. Okay, but if you are using in nanoseconds range, then we can there is no requirement of periodic refresh. Registers are used in computational structures. Dynamic registers are constantly clocked like pipeline data. So we'll in the next class we'll be seeing about pipelined data path and how pipelined registers work. But time being, we'll just say that dynamic registers are used where for high frequency applications. Like for example, if you see any processor, there will be the instruction queue registers, right? What are they doing? They are just fetching the instructions from the memory bank and storing it temporarily for the execution. Whatever present execution is completed, instead of waiting for that execution to complete and then fetch a data, a pipeline microprocessor, what it does is it prefetches the next instruction cycle and decodes it and keeps it in that in the instruction queue, right? So now if you see how long the data should be there in the instruction queue, if the microprocessor is working in even in megahertz, okay, then the data available in the instruction queue will be there only for few microseconds, right? Similarly, similarly when you have pipeline adders and all, we'll see in those registers, see the addition, the main ALUs, they operate at high frequencies. So the data in those registers, they keep getting refreshed in few microseconds or nanoseconds in a time. So in those kind of registers, we can use dynamic registers. Okay. So is this thing clear? Okay, let's move forward. So it will be very clear once we take the actual schematic. So this is the first kind of dynamic register which we are going to study today. It is just a simple two inverters which is connected through two transmission gates. Okay, now it is an positive edge triggered, so you are giving an clock bar. Now when the clock bar is low, so this becomes transparent. So whatever data D is available, that is available to the input of this inverter, and the output is available here. So it is available at this node, output of the node. And when the clock is going high, during the positive going edge of the clock, D gets isolated here, and this is getting activated. So whatever was the data available here now, it comes into the input of this inverter, and it is available here. Now D gets, Q gets slave to the D, which was sampled during the positive going edge of the clock. Okay, so this is a simple dynamic D flip flop where it is positive edge triggered. And now there is no C1 and C2 okay, which is connected externally. It is the intrinsic capacitance which is available at the gate of these inverters. Okay, so if you see here 1, 2, 3, 4, 5, 6, 7, 8, only 8 transistors are required out here. Okay, is this operation clear to all of you? Okay. Now if you see here, now if you use only an NMOS here transmission gate here and here, then you will require only 6 transistors. So you can do away with these PMOS transistors because anyway these inverters restore the level to full rail to rail, right? So the inverters will restore the level to rail output also here. So that is the reason why even an NMOS transistor will do, but using only an NMOS transistor will slightly affect the propagation delay, right? Okay. So only 6, then it is pretty low power than the static CMOS. So you will find those the net capacitance out here is pretty low. There is no short circuit currents, and static leakages are very minimal because there is only 2 inverters out here. The dynamic switching currents are pretty low here as compared to the static CMOS circuit. Okay. Now there are if you see the propagation delay, okay, the propagation delay out here will be, this is the rising edge of the clock. Okay, even before the rising edge of the clock, the data has stabilized here already. It is available at this node here, so that needs to be propagated to Q. So if you remember when we talked about propagation delay of a dynamic register, of any register for that matter, for any flip flop, it is the time taken from the rising edge of the clock till the output gets stabilized, right? So here this data which is available already when the clock is slow, so this doesn't contribute from path from here to here, doesn't contribute to any propagation delay here. Okay, so when the clock is going high, the data from here is being sampled here, okay, at this edge. From here now one transmission gate and one inverter. So the delay is one transistor delay plus one inverter delay. Okay, so this is what the it has got a pretty low propagation delay as compared to the static SIM registers, right? Okay, now what is setup time? Okay, the setup time, again, if you remember from the last class, we defined as the time before the positive going edge clock, the data should be settled, right? If the data is going to get disturbed beyond the setup time, then the correct data will not be sampled out here. So in this case, the positive going clock is available here. So now the data has to travel from one transmission gate to one inverter, and it has to reach here, right, when the clock is low. When the clock is low, this is transparent here. Now, so the total setup time, if you see here, is one transmission time and one inverter time. So if this clock is going high at 5 nano, and this is around both together put together is 0.5 nanoseconds, then if the data changes at 4.5 nanoseconds, 0.5 nanoseconds is the time taken here, and at 5 nanoseconds it is being sampled, so it will take the correct data. But if this data is going to change after 4.5 nanoseconds, then because this is going to take 0.5 nanoseconds here before the clock, this data is going to get changed after the rising edge of the clock, so you won't sample the correct data. So now here the setup time for this particular register is one pass transistor plus one inverter delay. Is this clear to all of you? Abhinav, is it okay? Murli? Yeah. Okay.
Sir, I have a question on propagation delay.
Yeah. Tell me.
You said it's only one pass transistor and one inverter, but it should be two pass transistor and two inverters, because let's say we are talking whatever we are inputting and what we are get at the output. So if the D is, let's say, for example, 1010 in that format, like every toggling thing,
Yeah.
then one we will get after like four delays, like transistor delay and two inverter delays, and zero again we will get after that,
Yeah. Now,
right?
no, the way we have defined propagation delay is we are expecting D to be stabilized before the setup time of arrival of the positive edge of the clock, and we have defined the propagation delay as the time taken for the output to get stabilized from the rising edge of the clock. Okay. Like you said, that much time it might take, but the way we have defined propagation delay is from the rising edge of the clock. Okay, so before the rising edge of the clock itself, D is stabilized till the midpoint. Okay, and then from there to the output, how much time it takes? Is it okay now?
Okay, but that D is actually D previous, right, sir?
Yeah,
The D.
yeah. Obviously, it is the D previous for a register. It is always a register. Always samples the output. If it is sampling the present input, then it becomes a latch, right? The register always has to sample the data which is just before the rising edge of the clock. Okay, only then it is known as a register.
Okay.
Okay,
Yeah.
that is an important requirement of an register, that it should not transmit the immediate data. Just before the rising edge of the clock, that data requires to be transmitted. So that is there. Okay. Clock jitter will have any impact? Yeah, it will have an impact. I'm just coming to that. Okay. So now if you see hold time here is nil. Okay, why it's nil? Because when the clock is going high, right, after the see, these are small intricacies which you should understand clearly. Why the hold time is nil? When the clock is going high, edge of the clock, how long should the data remain constant for it to function well? When the clock is going high, this is become non-transparent, right? So now even if the data changes, nothing happens out here, right? So that is why the hold time is nil. Okay, when the clock edge is going high, right, now you are permitted to change D, nothing would happen here. Okay, because my purpose is to sample a data which is previous to that, and how I am doing that is by disabling this particular transmission lag. The moment the clock is going high, I am disabling this particular transmission gate. Now even if the D changes, that doesn't get reflected here. Okay, so the previous data, whatever was sampled here, okay, that only will be available here. So that is how the hold time is nil. Okay. And then what is it? And also, could you out that the window that viewing the recording lecture later? No, I couldn't just understand. Could you just switch on your mic and tell me what is that issue? Yeah. Okay. Now there are one more issue out here. Here, if you see the dynamic positive latch trigger, okay, there could be who was it? There was an issue. Yeah, but wanted to know what would jitter do, right? So if you see here, this is 0 0 out here, and the clock, we know what is a clock jitter. Clock jitter is like both of this have to be perfectly synchronized here, but because of the uneven distribution line of the clock and the clock bar, there could be a possibility that the clock bar and the clock are not perfectly matched with each other. So this is known as a clock jitter. So in this case, there is a possibility that 0 0 that is clock is 0 and the clock bar is also 0 can happen. Okay. Similarly, a clock 1 and clock bar 1 also can happen for a small duration. Okay, this is an unwanted thing, but still it can happen in an practically realized layout. Okay. So what happens is, what is the problem in that? So if you see here, during 0 0 overlap, you have this PMOS being turned on, and this clock bar is also low, so this PMOS also is turned on. So this register becomes transparent. Okay, that is D is straight away available to Q. So if you remember, this is what a latch is, right? And the basic difference between a latch and a flip-flop is the flip-flop is never transparent. Okay, only during the edge the data is sampled and it is placed at the output. Okay, whereas a latch is totally transparent during a high clock, or depending whether it is a positive or a negative latch, it is totally transparent. And the drawback of a latch is, we know that it can result in a race around situation, which we discussed in the last class. Okay, so if it is transparent, it is not a good situation. It can result in a race around condition. Similarly, this jitter out here during 1 1, if you see here, during 1 1, you will find that this clock is this is enabled out here. Okay, because clock bar, so this will be enabled out here and this will be enabled here. So D will become transparent. So under both the circumstances, this entire register starts acting like an through and through latch, which results in latch. So that is a drawback of this particular configuration of dynamic register. So there are other registers which overcome these problem. Okay. So there is one more issue with this particular register, which is Q can change on the falling edge also. Whereas this is a positive edge trigger, Q should always be changing only during the positive edge of the clock, but it can happen that during the negative edge also the data can change. Okay, let's see how that happens. Suppose during the positive edge of when the clock is high, the data is changing. Okay, the data is changing. Okay, so normally if the data is changing, it is blocked by this right, by this pass transistor, and only when the clock is going high, this will be this will be transparent, and then it will be sampled. But in this case, what happens is, here suppose the data is changing, here the clock is going low here. So now when the clock is going low, this data will come here, right? It will come till here. But if it were perfectly synchronized, then this won't propagate further. But since there is a jitter here now, and this transistor gate, if you see, clock bar is still low, so from here it will get propagated, because there is a jitter out here, it will get propagated. So even in the negative going sample, negative edge also, there is a possibility of D getting transmitted to Q. So that is one more issue out here, right? So this particular issue, so there are two different issues out here. One is the register become transparent with jitter, and the second is the data being sampled during the negative edge of the clock. So these are two different issues. This second issue, there is a solution available, that is, now if you see here, this is the time, right, from here to here. So if you keep the total delay, okay, or intrinsic delay out here of one pass transistor plus one inverter plus one more transistor, greater than the jitter time, okay, or in other words, if you keep the jitter lower than one pass transistor, one inverter, and one more pass transistor delay, then in the negative sample, it will not get sampled out here. Is this aspect clear to all of you? Right. So if you see here, okay, the data is changing out here, okay, here. Now that data is coming here, and it is coming here, okay, one pass transistor, one inverter, and one more inverter out here, right? So when this negative edge is going out here, right, when in the negative edge, this data whichever has got changed in the negative edge, if it whatever has changed will come here, okay, it will come here and it come here, and then the positive edge is here. So during this time, this is also transparent, right? So if you keep these three delays combined, okay, more than this particular jitter time, then it will this negative sampling at the negative edge of the clock can be avoided. Okay, so so this problem has been avoided, but still during the jitter, this register being transparent, that remains a problem. So we have some other circuits which are better. Okay, but still it's a dynamic only, but we have something better. So this is the second topology which we are going to discuss today. This is known as Clock-Skew insensitive C-square MOS register. Okay, C-square stands for clock and clock bar, both are required here. Okay, C-square MOS register, if you see here. Okay, now this is a master, and this is an slave register. When the clock is low, okay, when the clock is low, you will find this clock is low. So this, excuse me, this gets switched on, this is also getting switched on. So this acts like an inverter. So whatever data available here will be sampled, and it is available at node X. Okay, so don't think there is a capacitor out here again here. Okay, this is the intrinsic capacitor, parasitic capacitance of the gate of these transistors and the interconnects, and the here from gate to drain of these transistors. So this CL is an sum total of all the intrinsic capacitors. So there is no additional capacitor which is put here. Okay, just for explanation purpose, to visualize that there is a node here and there will be some capacitance, this has been put here. Now this data D, when the clock is low, this becomes an inverter. This becomes just an inverter. Okay, this data is sampled here, whereas this acts like an tri-state buffer in a high impedance state. Okay, because these two transistors are on, whereas M4 and M8 are off. So whatever was the previous data, that will be retained here, because M8 and M7 are off. So this is a nothing but a tri-state buffer, right? So it is in a high impedance state now. So data is sampled here. Now in the positive going edge of the clock, right, in the positive, just when the clock is going high, right, this will be isolated. This will be isolated, and this will be sampled. So it is like, it is not an through and through, right? It is a positive edge triggered flip flop, right? So during the positive edge of the clock, this data will be sampled, and now it will be available at Q. So one inversion and second inversion. So you get back, you have D bar here, you will get back a D out here, right? So these are inverters, right? So this is how an Clock-Skew insensitive C square MOS resistor works. Now we have not discussed why is it that the Clock-Skew it is insensitive to Clock-Skew. That means Clock-Skew is not going to affect its operation. Now why is that happening? So let's discuss that now. Now, if you see here, so let's take up the first condition, where you have a clock also 0 here, and the clock bar also 0, right? So if the clock is 0 out here, so when the clock is 0, this is the condition, right? So this transistor, okay, will be off out here, right? This transistor now this transistor will be on out here, right? So for 0 0 overlap, right? So now if you see here, now D is not transparent out here, although these two transistors are on at the same time. Clock is 0, so this PMOS is on, NMOS is off. So whereas this NMOS is off. Now if you see here, what can happen? Like suppose this initially, when the clock is this is 0 out here, right, and because of this Clock-Skew, right, this is going to get charged. This data is if D is 0, this will get charged to 1, right? So this will get charged to 1, and this transistor will get switched on. So that transient will not be reflected at the output node, because there, see, this transistor is not available there. Okay, for example, if this is already at so what can happen at this node during 0 0? This node, if it is 0, it can get charged to 1. Right? If it is 1, it cannot get charged to 0, because this transistor is not there. So only one thing can happen here during this 0 0. That is, if it were a 0, it can go to 1 because of the jitter out here. So that is the only, this 0 can flip to 1. Okay, and what will happen in the next stage? This transistor, which was off initially, can get switched on to 1. Okay, but here there is no this transistor remains off, so the output doesn't get affected, right? Like this is getting from 1 to 0, okay, will not affect the output, because this PMOS, okay, if it were like if it were 1 if it were 0 here, this would be 1. So if this PMOS get switched off also, this will continue to remain 1. So this output doesn't get affected because of this both the clocks going low. Is this aspect clear to all of you? Is it confusing, or is it clear? Anybody can just put it in the chat box, so that, yeah, okay, not clear. Okay, good. See, what can happen? Yeah, I know. This is a little bit confusing, but if you listen carefully, we should be able to. Okay, let's try and understand here. Suppose, let's assume before the clock, when the clock is high, okay, before the clock is high, this node is charged to 0, and this is charged to 1. Okay, that could be the condition. When the clock is going low, when the clock is going low out here, right, when the clock is going low here. Now the clock bar is also going high after certain jitter out here, right. So in that case, in a normal operation, what would happen, right? If you both these are synced, when the clock is going low out here, like this will get switched off out here, right? Because this is off, and this PMOS is also is going to get switched off. But in this particular case, because of this jitter, this NMOS and this PMOS, okay, they will be this PMOS, this PMOS M4 and M8 both will be on simultaneously. That never happens normally, but here it happens in 0 0, right? Since, see, if you see here, let me go back to here. This PMOS and this PMOS can never be on simultaneously, because one is clock, one is clock bar. Alright, here this NMOS and this NMOS cannot be on simultaneously because both, one is clock bar and one is clock, right? So this M4 and M8, only one of them should be on, and M3 and M7, only one of them should be on at any given circumstances, provided the clock and clock bar are perfectly synced with each other. Okay, now here if you see here, what is happening is because they are not synced, you have a clock also 0 here, and the clock bar also 0. Both are zeros here. Okay, since both are zeros, it will result in a situation where both these PMOS are on. Okay, now if both these PMOS are on, what is it? We said the D should not be transparent to Q. Okay, that is what the was the drawback in the previous case. If both are on, then D becomes transparent to Q. So whatever available in D should not go to Q. So in this case, suppose D was 1 initially. Okay, let's take an case 1. Now since during this clock jitter time, if D is making an change from 1 to 0, during this time D is making a change from 1 to 0. Since it has gone to 0 here, this node will now get charged to 1, right? Because D is become 0 here. Now this MMOS turns on, this node gets charged to 1. Now this 1, okay, if it is getting charged, it will switch on M5. But switching on M5 will not really affect the output at Q because this NMOS is off out here, right? So now D is not transparent to Q, right? So it is although D is making a change from 1 to 0, that doesn't get reflected to Q, and whatever was the available data Q previously, it will still try to hold that. Is it clear now? Okay, let's see. Okay, same thing happens here when 1 1 D changes from let's take that condition also. Suppose D is 0 here. Okay, suppose D is 0 here, then initially, and this is 1 out here, right? If this is 1 here, just before this clocks getting switched on, so if it is 1 here, it will be 0 here. So there is no this is 0 out available here. Now D is changing from 0 to 1, right? So this node doesn't get affected because there is if it is changing from 0 to 1, okay, there is no NMOS out here, so this node doesn't get affected. So this will continue to remain in 0. So whether D is changing from 0 to 1 or 1 to 0, this output remains a constant out here. Okay, is it an okay? Yeah, okay. Now in the second case, where 1 1 case also, in the 1 1 case, both M3 and M7 will be on out here, right? So M3 and M7 will be on. So let's assume initially D was 0 out here, right? So this will be 1 and this will be 0 out here. Now in case D changes from now 0 to 1 out here, so this transistor will be switched on and this node will be pulled to 0. So if this is pulled to 0, M6 will turn on. But M6 is turned on, but you don't have this PMOS out here, so this will not get charged to 1. So it is isolated now here. So now D is again not transparent to Q. So if you take the other condition where D was initially 1, then this will be 0. So this would have been before the clock going, this would have been 1 here. So in that case also, if it is going to change from 1 to 0, this is going to get switched off. This continues to retain charge. So in all the conditions, D is not transparent at all. Right. So by having this kind of thing, we can make this D transparent proof, so it will not act like an latch out here. Okay. Yeah. Now but there is an small problem out here also. So if you see here, suppose like we said that initial thing, like D in this case is going from 1 to 0 here. So when it goes 1 to 0 here, this will change a state, right? This will change a state. But then when the clock is going high, right, this is going to bring in this cut in this transistor, and when that transistor is getting switched on, now the change is going to get reflected at Q. Okay, although during the overlap period, this data is not reflected here, right? But when finally this thing settles down, this data, because this node has got changed, right? This node has got changed during this duration. During this duration, the output X has got affected. Only thing is that has not got reflected at the output, okay, because we didn't have this transistor here. But subsequently, when the clock is going high, right, when the clock is going high, this will get an whatever node is output is available, and inverted will be available here. Okay, so that is an issue with both here, both these issues. Okay, so although it is not transparent, but when the clock edge is going high, so it will update the data which is available at X to the output. Okay, so that is also not a desirable thing. For that, again, what we need to do is, so before the rising edge of the clock, right, we have to have something known as an hold time, setup time. So we should not change the data. Okay, so one inverter delay is required for this data to reach here. So before going, so during this transition period, you should not allow D to change. Okay, so if you do that, if you put a constraint of hold time, okay, which is equal to the jitter, then this during the positive edge of the clock, so that issue of the new data being sampled can be avoided. Okay, for the new data means register should always sample the previous data. So if you don't allow D to change during the jitter time, then only the previous data will be sampled. So that is the second problem can be. The first problem is as such eliminated, it is not transparent. The second problem of data D changing during jitter being reflected at the output can be avoided by imposing a constraint of hold time, in which during the positive edge of the clock here, right, the data should not change for this much time, right? So that by the time this clock falls down, if you are holding this data out here, then you will not have an jitter. Okay, so you see here, now this is the positive edge of the clock, right? So during this jitter period, if the data is remaining constant, then that problem of new data being sampled can be avoided. So this is how this particular, till we saw in the last class a few of the registers where there was no hold time constraint. Now if you see in this particular configuration, we only had setup constraints. Now here we have a hold time constraint also, we are imposing it. so that this particular register works fine. So this is not a very big problem. Once you have estimated your clock jitter, then when we do the static analysis, we will impose this. In the next class, we'll see about static analysis, timing analysis, where we are going to impose this hold time constraint. That means the data should not change. This is the positive edge of the clock till the clock bar goes low. So this is the jitter time. So if as long as the data doesn't change during this time, then this would work perfectly fine. Okay, so this is known as Clock-Skew insensitive C-square MOS register. Right. Okay, another constraint is there, that is the rise time and fall time of the clocks and clock bar signals. Okay, should be this is an empirically through simulations it has been observed that it should be 5 times smaller than the propagation delay of the register. So obviously you can see that if the clock is very the rise time is very high and fall time is very high of the clocks, so the data can get corrupted, right? Because it is actually if the clocks are going in a very slow rising and a slow falling, you are actually introducing jitter in one way, you can call that. So that can corrupt your data. Okay, so that is one restriction. Okay. So you have another kind of registers, dynamic registers, which are known as dual edge registers. Okay, in which during the positive edge of the clock as well as the negative edge of the clock, the data is sampled. Okay, so if you see here this particular register, okay, these two together, it is an negative edge, because during the positive edge D is sampled here, and then during the negative edge that here you have a clock bar, so the data will be available here. So these are two latches. This is a positive latch, this is a negative latch. So you have a negative edge triggered data being sampled here. Parallelly you have one more registers, a set of registers here. Now this appears to be incomplete, but these two transistors can be avoided because you are connecting N1 here and N2 here. Now if you see, the clocks are now complementary clocks are given here. For the NMOS you are giving a clock bar here. So when the clock is low, this D will be available at Y node when the clock is low, and when the clock is going from low to high, during that edge the data will be sampled and it will be available here, right? So if you see here, these two outputs you are shorting out here, but when the clock is high, this is in a high impedance state, and when the clock is low, this is in a high impedance state. Okay, so shorting is like it is connecting two tri-state buffers, so that is very much possible, like we do in multiplexers. So what happens in this whole scenario is that D during when the clock is low, D is available here, and D is available at Y, and positive going edge triggered, this will be sampled and available here, and when the clock is high, then D is sampled at X node, and negative going edge, this is going to sample this data and put it at Q here. So in both positive edge and the negative edge of the clocks, the data will be sampled. So it has got certain advantages. This input sampled on both edges, low frequency for same functional throughput, and power savings in clock distribution. So these kind of circuits are also used in modern day microprocessors, okay, for certain applications. Okay, now we have something known as a true single phase clock registers, right? So here if you see, we are not using clock and clock bar here. Okay, we are using only that is known as true single phase clock, right? That means sir, can you explain the importance of lower half of the circuit again? Let me go back here. Okay, now let's see when the clock is low. Okay, when the clock is low here, this whole thing is in the off state, right? This is in the off state. So just before the clock is going low here, right? Whatever was data available here, okay, this is clock low, this will, so this data just before the clock is low, it will be sampled here and available at Q. And when the clock is low, if you see here, this transistor is on and this transistor is clock is low, right? So this both are on here. And what is N1 here? N1 is here, right? So whatever is the data D available, so this acts like an inverter. So D will be sampled and available at Y. Okay, but this is off now in this particular condition. Okay, because the clock is low here, right? And when the clock is going positive edge, then this Y will be sampled and available at Q. Right, so this is like the upper 2 is like an flip-flop working on negative edge triggered, and the lower half is acting like an flip-flop which is positive edge triggered. Right, when the clock is high, this data is sampled here. When the clock is going low, in that during that edge, this is given out here. Similarly, when the clock is low, this data is sampled here. During the positive edge of the clock, this data will be placed at Q. Is it Akash? Is it okay? So this is actually kind of multiplexing the positive edge and the making parallel flip-flops connected together through high tri-state buffers, okay, which are given complementary clocks. Okay, now we said now the purpose of this particular is a better circuit, because the single clock is used out here, right? Clock, you will find clock is given here, clock is given here. Now what happens if the data is 0, right? Suppose the data is 0 out here, right? What happens when the clock is 0 out here, right? When the clock is 0, then both of these things they remain off. The data is in the hold position. When the clock is going high, right? So if the data is 0, then this node will get charged to 1 out here, right? If it gets charged to 1 here, so this 1 will get, because this transistor is going to switched on, and this will be charged to 0 out here, right? So when the node data is 0, 1 is charged to high, and this is going to be charged to 0 here. If the data is no similar, when the clock is high, we are talking about when the clock is high, and if it is 0 here, if the clock is high here, this will be charged to 1 here, right? But this clock is high, but this transistor is off here, right? So this is 1 here, this clock is high and this transistor is on, this will be charged to 0 here. Now if you see here, from here to here, yeah, okay. So this is actually two inverters. So you have to keep reminding me to reduce my pace. Okay, so they are two inverters. When the clock is high, it is just like two inverters which are connected and back to back. Okay, so there is no issue here, right? So back to back inverters connected. But when the clock is low, okay, and when the clock is low, any change in D should not be reflected at the output. That's how an latch works, flip-flop works. Like when the clock is low, right? When the clock is low, nothing should happen here, right? So now let's take a situation like where the data is 0 out here, right? And so initially, suppose the data is 0 out here, right? And then this was 1 here, this was 0 here. Now the data is changing from suppose 0 to 1. So this will be switched on in that particular case. But since the clock is off, okay, so this is not going to affect this 1 out here. The output continues to remain there. Now if the clock is low, suppose initially this data was 1 here, then this would have been 0 here, this will be 1 here. Now the clock is going from 0 to 1, right? So from 1 to 0. So now what happens is this node will get charged to 1, right? But since the clock is off here, this node cannot be discharged to 0. So if you see here, when the clock is 0, then the data is not transparent. Okay, let me repeat it here once again. When the clock is high, with the first case is when the clock is high. When the clock is high, so these transistors are switched on. So you can just think of these transistors not being there. So you have one inverter driving the second inverter. So the output is an input, whatever is there is available at the output. So there are two inverters which are connected back to back. Okay, but when the clock is low, okay, when the clock is low, so there could be two different situations, right? There could be two different situations. Okay, first, when the input is initially it was 0. Assume initially the input, data was 0. So it was 0 here, it is 1 here, it is 0 here. Now from 0 to 1, it's making a swing. If it is making a swing from 0 to 1, this transistor will switch on. But this node 1 will not get affected because now clock is 0 here. So this continues to remain 1. So the output is not affected. Okay. Now there could be, let's take the second situation where before the clock going low, this was 1 and this was 0. Right, and this is 1 out here. Now from this is making a transition from 1 to 0, and when it makes 1 to 0 here, so this charge, it was 0 earlier, so this will get charged to 1 here, right? So this will switch on this NMOS, but then since this clock is low here, that this output node will continue to remain 1. So if you see here, in both the cases, this D is not transparent to the output. Okay, now there are other conditions also. So suppose the clock has gone high here, right? And now if you try to analyze, the clock has gone high. Okay, now the data is changing. Does it get reflected at the output? Okay, no, is it going to be transparent or not? So that if you see here, when the clock is high, so any change in the output, it will be transparent in this particular case, right? Because two chain of inverters, latch is transparent and Q is slave to D. So this works as an latch in that particular case. So that we need to be careful here, right? In this particular case. So it is not an resistor, it is just an latch out here, right? Okay. So what we do is we take an 10 minutes break out here, and we'll revisit from this slide onwards. Okay, so just going before the break, we were discussing that how an true phase clock register looks like. This is not a register, this is just an latch out here. Basically, when the clock is high, this is one inverter connected back to back inverter. So whatever is data when the clock is high, whatever is the data which is being fed in will be available at the output. And when the clock is low, suppose the data is making a transition from 0 to 1, this transistor will be switched on, whereas this transistor is off, so this node will not get affected. Okay, whereas if this is making from 1 to 0 here a transition, this node will get charged to 1. If it were 0, it will get charged to 1, but that doesn't get reflected here because now this is getting charged to 1. So this transistor will switch on, but you have this clock is off, and hence so this acts like an positive latch. Okay, positive latch means the data will be transparent when the clock is high, right? And like we so to make a register, like in the we learned in the case of a normal static latch, how we converted into a register was by cascading a master slave two latches, right? One was used as a positive latch and one was used as a negative latch. The same thing here. Now you have a positive latch here and you have a negative latch here. So if you cascade these two, then you will get a negative flip-flop here, right? So during the positive edge of the clock, this data will be sampled and it will be available here. when the clock is going low, during that negative edge, then this will become opaque, like these two transistors will switch off. But whatever data was available when the clock is going low during that edge, that will be reflected now out here, because this is a negative clock out here. So for the negative clock here, we have not used a clock bar, okay, unlike in the previous case, we are using an PMOS transistor out here. So that is the difference, that we are using a single same phased clock in both the positive latch and the negative latch. Now one difference, if you note here, when you are using an NMOS here for the positive latch, you are taking the output from this node and not from this node here. That is because NMOS is a perfect transmitter of 0, and hence if you connect it here, there won't be any problem, because this is a PMOS which is going to pull this node to high. And whereas when we are using an PMOS out here, so we are taking the output from the node below the PMOS here, from the drain of the PMOS out here, so that it gets charged. You will get a full rail to rail output at both these two nodes. So you have an positive latch and a negative latch. So when we cascade these two, it will act like a flip-flop, which is being triggered at the negative edge. Now if you want a positive edge triggered in a flip-flop, then the positions of these two have to be swapped. Okay, so now here, if you say in two-phase clocking schemes, care must be taken in routing so that the clock signals to ensure overlap is minimized here. But here it's not an issue, because we are giving the same clock. There is no clock and clock bar, and a register can be constructed by cascading a positive and negative latches. Main advantages is use of an single clock out here. Okay, the disadvantages here is the number of transistors. Now 12 transistors are required now for this. If you see, the number of transistor requirement has gone slightly higher than the as compared to the earlier dynamic latch. Okay, there if you see here, we just used 8 transistors here. So in this particular configuration, now around 12 transistors are required. So 4 more additional transistors, but we are avoiding that clock jitter issues, because we are giving the same signal out here. Okay, clock and clock everywhere, we are using a single phase clock. So another major advantage of this particular circuit is out here is we can incorporate logic also out here, right? Instead of an pure like a D register, this is some logics also can be incorporated. For example, this has to be the for an positive latch. Here you can put an pull-up network, and you can put an complementary pull-down network. So if you see here, for the same delay, right, instead of having a latch and then a combinational circuit, this is a mix and match of a latch plus a combinational circuit. So it saves a lot of space and time, right? Okay, now if you see here an AND latch, if you see here, now input is given here, two NMOS transistors are connected in series and two PMOS are connected in parallel out here. So if you see here, this is an NAND gate, right? So if you see here, when the clock is going high, unless and until both the signals are high, only then this node will be 0 out here. So this will act like a NAND gate, right? When the clock is high, this becomes an NAND gate, and then you have one more inverter out here. So this will become an output available here will be AND. So when the clock is high, if you see here, this is a NAND followed by an inverter, so it will become an AND gate. Okay, so this entire thing will act like an AND latch now out here, right? So again, you can have this is a positive edge latch. Again, you can have a negative edge latch cascaded with this to make it a flip-flop. So is this aspect clear to all of you? Anubhav, Chandan, is it okay? Right? Okay. So if there is any doubt, please feel free to interrupt me. Okay. I have not enabled the mic. Yeah. Yeah, I think the mics are enabled. Okay. So this is how this is another advantage of an TSPC registers, where we can not only that we are using a single clock, but also we have an added advantage of incorporating logics also into the register. Okay. This is again including logic. So if you see some simulation was done here, in which in 250 nanometer technology, those setup time it required 140 picoseconds with this particular configuration, whereas if they do it in a conventional approach by a AND gate followed by a latch, if you do, then total 600 picosecond was the setup time required in that particular case, right? So if you find so this is just a result of one of the simulations by using an integrated and a latch together. The setup time observed was 140 picosecond, whereas if you have a separate and followed by a latch, in that case 600 picosecond was the setup time observed. So it just this statement has been this simulation result indicates that we can save upon the propagation delay by incorporating logic in the register itself. Okay, and that is possible in TSPC registers. Okay. So this is another complexity can be further reduced by not having the clock in the second stage. Okay, here if you see here, if you the second stage also there was a clock here. Now that has been removed out here. Okay, so the only issue here, you can save one transistor out here, but the performance, there will be some degradation of the performance, because if you see here, it is an NMOS here. Now you got to take the output from here, so you don't have full VDD here. So this will not be driven completely. So it will whole VDD is not available here. VDD minus VTN will be available in this particular case. Okay, so if you see here, when the clock is high, this becomes an inverter. We are taking an input from here, right? So now you have an NMOS here, so whole VDD will not be available here. VDD minus VTN will be available here. So this will operate and not operate as fast, because you are not giving the entire overdrive voltage which is normally available. So this will operate slower. So at the cost of performance, we can reduce one transistor out here. Okay. So this is one particular configuration which is not very widely used, because speed is a major issue in all these circuits, right? Okay. So this is an positive edge triggered register. Another configuration of out here, where you have a D. You see here the clock is given here. So when the clock is low out here, so the data is sampled and available at X out here, right? So when the clock is 0, what happens? Okay, this is slightly a small variation of the TSPC. When the clock is low, there is certain additional advantage out here. We'll see that. So when the clock is low here, right? So when the clock is low here, this M2 is switched on, right? This is an PMOS. So this acts like an inverter. So whatever is D, inverted of that is available at node X. It is available at node X. Okay, so that is the first. In the first stage, D is sampled and it is available at node X. What about the second stage? If you see the second stage, this is clock is 0 out here, right? So this is off. This will be on. So irrespective of what is available at X, this node will be pre-charged to 1. Okay, so this is pre-charged to 1. Right, so now if you see here, this particular node, and it is like a dynamic CMOS node, where this node will be pre-charged to 1 when the clock is 0. So and what about this, the third stage? In the third stage, the clock is low out here, so this M8 is an isolated out here. So you will find whatever is the charge available here. Okay, this is going to be pre-charged to 1, so this also remains off. So this will retain whatever value was there earlier. So a Q also will retain the value which is available here. So when the clock is 0, now what happens to each of these stages? Let's discuss once again. When the clock is 0, this whole starts acting like an inverter. So D bar is available at X. Okay, that is on point number 1. The second point is at node number X, right? This is off, whereas this is on. So irrespective of what is available at X, so Y will be pre-charged to 1. Okay, this is going to be pre-charged to 1. What about this stage? This is going to be in high impedance state because clock is off out here, and this is pre-charged to 1, so this will also be off. So this is in the hold state. Now hold state means whatever was the previous data. Now remember, we are talking about dynamic resistors, and that is why this whatever charge was available at the input gate capacitance, that is expected to be available here, because we are talking these resistors are designed to operate only for a few nano or microseconds. So whatever charge is available here, inverted of that is available here. Okay, now during the positive edge of the clock, so this transistor will be switched on out here. So this output, if X is 0, then this will continue to remain 1, and if X is 1 out here, then this will be discharged to 0. So that is what happens in a dynamic circuit, right? Whenever Y is pre-charged to 1, and depending on the logic, it will be either discharged to 1 or that 1 remains here. So here also, if you see, it is going to be discharged to 0 in case X is 1, otherwise it continues to remain at 1 out here, right? So now, and in that case, now this clock is going to be switched on here, so this becomes an inverter. So Y bar, and then again this will be available here, so the D will be available here. So during the positive edge of the clock, D bar was available here. Now you get D again here, D bar here, and D is available here. So during the positive going edge of the clock, now whatever is the data available here, which was that gets sampled, and that is the value which will be available here. Sir, what is the value of D we are considering here? Whatever may be the case. Okay, when the clock is low, whatever is the value of D is available till X, till point X, D bar will be available here, right? And when the clock is going high, and when the clock is 0, Y is pre-charged to 1 here, and in case D is 0 here, this will be 1 here. When the clock is going high, this Y will be discharged to 0. In case D is 1 here, then it will continue to remain 1 here, because M5 is off. So D is available here till the clock is low. When the clock is going high, D gets reflected onto Y. Okay, and when the clock is going high, this turns on. So you have now D gets connected to Q through two inverters. So now D is again available at Q. Is it okay? So if you see here, so this is how this works. So this is a positive edge triggered and flip flop here out here in this particular case. Okay. Now whole time, now if you consider these three, now on the positive phase of the clock, on the positive, when the clock is going positive, okay, so this X is being sampled to Y, right? When the positive edge of the clock is, when this is going to the, we are talking about the whole time. When the clock is going high, if X were 1, then Y requires to be discharged to 0, and if it is 0, then Y continues to remain at Y. Okay, that is the condition how this works, right? So so how long X should be stable, or D should be stable, is when the clock is going high. If it were 1, then it should allow this Y to get discharged completely, right? So that means this X has to remain constant till this Y gets completely discharged, and hence we can say that the hold time is a 1 inverter delay. Okay, so the hold time, so D should not change during that period, then this Y will not get discharged completely. So in this case, the hold time of this particular circuit is 1 inverter delay out here, right? Is it understood? When the clock is going high, right, X is available here already. Okay, that is the setup time. We'll talk about that later. X is already available here. We are talking about the hold time. Hold time means whenever the clock is going high, should the D, what is the time available for D to change now? Now when the clock is going high here, okay, this was pre-charged to 1. So in case X is 1, so then this Y has to be discharged to 0. So you can say that X has to remain constant, because if while it is being discharged, if D changes, then the correct data will not be transmitted. So X has to remain constant for 1 inverter delay time. So that is why the hold time is 1 inverter delay. Okay. What about the setup time? Now setup time also, if you see here, when the clock is going high, that is the time X has to be stable here, right? So this what the D has to get transmitted from here to here. So before the going of the clock going high, this D has to reach the point X. So the setup time is also on a 1 inverter delay. So if you see here the delay times earlier in the other registers where we discussed, where the setup time was greater, right? 1 transmission gate plus 1 one transmission gate plus 1 inverter and all. Here the setup and hold times are only one inverter delay time. So this is the advantage of this particular scheme, right? So the setup time is 1 inverter delay only. Now what about the propagation delay? Now the propagation delay of this is actually, if you see from X out here, right, it has to come to Y, and from Y it has to come here, and from here it has to go here. So the total propagation delay is slightly higher here. It is 3 inverters, okay, from here to here, here to here, and here to here. So the propagation delay for this particular schematic, while the setup time and the hold times are very less, the propagation delay is slightly on the higher side. You have 3 inverter propagation delay, okay, for this particular schematic. Okay, there is another issue out here with this, but it has got other advantages, right? We are talking about a single same clocks, without clock and clock bar, and it is jitter free, so jitter resistant. So you can see the advantages are very many, because we are in these circuits we are using a single clock, so all those jitter issues are not here. So so this small little bit of one additional gate delay is not much compared to the other issues. Okay. Now here there is an other one small issue which we have to see. The sizing is critical in this case. If you see here, suppose this is pre-charged to 1, and now it is pre-charged to 1 when the clock is going high, right? Since it is 1 here, it is 1 here, this clock is going high, so this will start, this node will start falling down. So if you see, this node is falling, this red line which is shown here. So Q, so this will start falling down, and suppose this is 1 here, this will also start falling down, and once this starts falling down beyond a certain level, M7 will be switched off and M9 will be switched on, and then again this Q will start going up here, right? Is this part understood? Let me explain once again. When the clock is low, node Y will be pre-charged to 1, right? And this is suppose this is holding 1 here. Previously this was holding 1. We take that particular condition. Now when the clock is going high, right, because this is 1 here, this Y starts falling down, but this is 1 here initially. Since it is initially 1 here, so this charge will start falling down like this, right? Okay, it starts falling down. So since it is falling down here, but then subsequently when Y falls down, M7 will be switched on and M9 will be switched on, and this will get charged back again here. So it will get charged back. Now if you see in the output here, Q, this red line, there will be a glitch. Okay, since so there will be a glitch available at the output. Okay, so to avoid that, so this was the initial the sizing, like M7 and M8 were 2 micro, whereas M5 and M4 was 0.5 micro. Now to avoid that, we need to make these transistors slightly weaker as compared to M4 and M5. Now they were kept in the same size out here. Now if you see here, in this particular case, this discharge is happening slowly. This is happening slightly on the faster rate. So you will find this is not falling as much, right? It is not coming below half VDD or the inverter threshold. So the output has remained constant out here in the modified version, right? So you to avoid this glitch, so you need to keep these sizes even equal in this particular simulation. Even equal is good enough, because even if it is kept equal, you find Q is falling a little bit out here. But then it is not falling beyond the threshold voltage of this inverter, so Q is stable, right? If you don't want even this much fall, then you can probably increase the size slightly more than this M7 and M8. Even if you keep it equal, there will be a small glitch at this node, but that doesn't get transmitted at the output. Okay, so this is a thing which you have to take care while doing the sizing of the TSPC resistors. Okay, so now you have a small 2 more circuits which we will discuss now. One is known as a pulse resistor. Okay, a pulse resistor is nothing but you have 2 inverters which are cascaded, and we are giving a very small pulse to the clock. So this is actually if you give a large clock out here, it will become a latch. Okay, so right, this will be on, this will be on, so 2 inverters cascaded with one another, so it will become a normal latch. But we are calling it a resistor because we are giving a small very small signal here. So it is like momentarily we are sampling it in the positive edge, we can call that. So this is known as a pulse resistor. We are doing a small, so you can, so race around can be avoided, because this duration, clock duration is not a clock, but it is known as clock G. Okay, clock G means G stands for a glitch. Okay, now so this is an glitch generation. It is small glitch or a very small spike. Okay, here it exaggerated is shown here. Okay, it won't be this much, it will be even it's going to be kind of a glitch here. So during that glitch, the D will be sampled and available at Q. So it will act like an edge triggered flip-flop. Now how to generate this glitch? You see here, now initially with the clock is 0 here, so this PMOS will be switched on, so X will be 1 here, and since the clock is 0, this output of the AND will be 0, so it will be 1 here, it will be 0 here, so this NMOS is switched off. So this NMOS is switched off, PMOS is switched on, so you have 1 available here, right? And when the clock is going high here, right, this PMOS will be switched on. So but at that instant this is not yet switched on, so you have both 1 1 here, right? So this 1 1 will create a 1 here, this 1 will create a 0 here, this 0 will create a 1 here, and now that one will switch on this transistor out here, and this node will get discharged to 0, and that will put in 0 here now. So that will make this output to go to 0. This will be 1 here, it will go to 0 out here, right? But so if this is going to be 0 here, so now that is a stable condition. Now it will remain so till the next clock again arrives. So you will find how this glitches. So this duration of this glitch can be set by the number of inverters which you use here, right? If you use a larger number of inverters, then this width can be this can be increased. Okay, sure. See, well, this is an D. This is inverter. This is a second inverter. If you give a clock high for a long time, then this becomes a latch. Okay, but a flip flop, if you give this as a very small, a few picoseconds or few picoseconds spike here, and then it amounts to sampling the data from D to Q at that edge. Okay, basically we are giving a, this is an exaggerated figure out here just for explanation purpose. Otherwise this can be a very small narrow pulse. Okay, so this now can be treated like an register. Okay, is this much understood? Why we are calling it an register? How? Okay, because we are using a very narrow pulse. Now how to generate that narrow pulse? Now if the clock is 0 out here, you will find here this PMOS will be switched on, so the node X will be charged to 1 when the clock is 0 at this stage, a steady state condition we are talking about. So it is 0 out here. Here also it is 1 out here, but since this node is 0, you will have 0 here, you have 1 here. Okay, and then you have a 0 out here. So this NMOS transistor is off. So this is 1 and this is 0 here, and this is in a stable condition. Now when the clock is going high, okay, when the clock is going high, the input to both the AND gates will be high. Okay, because this X was charged to 1. And for it to get discharged to 1, this has to be switched on. Now this is not yet switched on, so this has gone 1 here, so this will become 0 here. Now this will become like both have become 1 here, so this will become 1 here, 0 here, 1 here. Now this will be switched on. So this will be switched on after a propagation delay of 1 AND gate and 2 inverters. So the moment this gets switched on, this AND this will become 0 and this will become 0. Output will become 0 here, then this will become 1 and this will become 0 here. So you will get a small glitch. Is it understood? So this glitch period, in fact I think it is taking 2 rotations, right? This duration can be set by increasing the number of inverters here. If you use just 2 inverters, it will be a very small glitch. Okay, is it understood? Okay, thank you. So now if you see here, the propagation delay in this case is obviously from D to Q. When the clock is going high, it is a 2 inverter delay. Okay, setup time is nil. Okay, because when the clock is going high here, D is being sampled here, so there is no setup time. So D should be whatever is available in D, that will be sampled. So there is no setup time. Hold time is the glitch time. Okay, glitch time means this duration is known as the why are we generating glitch? We need to avoid glitch, right? Yeah. It is because this is being triggered by a small pulse. The functioning of this particular resistor is based on we are generating this glitch as an input. We are using an from a normal clock, we are making an glitch clock to trigger these 2 inputs. Okay, yeah. Okay, so that is why we are generating this glitch is nothing. This clock G, we are feeding it here, right? Okay, so this is the circuit to generate the clock for this particular circuit. Okay, now hold time is the glitch time. That means for this much duration, when the clock is high, D has to be stable. Otherwise, can you please tell the use case of this circuit? But the simulations we won't get. We'll be able to simulate these circuits. We can generate these kind of in the simulation also, right? So if you see here, this register, now if I talk about the advantages, it is again one, the number of transistors used is here only 6, right? The second advantage is it is both the you don't require clock and clock bar signal. So till now, the first circuit which we discussed, it required a dynamic register required 8 transistors, but clock and clock bar signal was required. Then we saw about the TSPC signal registers in which only clock was required, but the number of transistors required was higher. And now we are talking about an register in which the number of transistors is also less, whereas and single phase clock is also used. Okay. So but the disadvantage is verification. So when in the verification, many a times we give test vectors and then we see the outputs at intermediate states. So now that testing and verification becomes an complex issue. Okay, in these kind of registers. How can we increase the duty cycle of the glitch? Okay, that is by increasing the number of stages out here. Right, if you increase the more number, if you put more inverters out here, the glitch duration can be increased. Okay, so that is this. Okay, now this is the last kind of amplifier which we are discussing today. It's an sense amplifier register. What is the advantage? Like I told, what are the advantages here? One, we are using a single clock. We are not requiring clock and clock bar, and we are using lesser number of transistors out here, right? And this particular circuitry is not only specific to this. This is used to trigger a number of registers. So we don't count the number of this is a clock generating circuit separate. So if you see, just if you look at the particular only the register, then there is only 6 registers out here, 6 transistors used for making a full flip-flop. Second, we are using the same phase clock here, right? So that are the advantages. Now this is an sense amplifier register. Okay, now this is generally used where you have memory cells in which dynamic memory cells where you have the bit and bit bar lines, right? So you can't connect the main data line onto those memory cells, because those data lines which are there connecting the memory to the microprocessors and all will have huge capacitance, interconnect capacitances also. So if you try to connect those lines directly onto your memory bit and bit bar lines, the data will get corrupted, right? If you tear a one, because the moment you connect a big capacitance and switch on a big capacitance onto those lines, the data could get corrupted, like it could flip, the data could flip because of the huge. So these kind of this is a kind of amplifier, sense amplifier only, register based. So this is now how does this function here is when the clock is low, obviously this M1 is off, so you have these 3 transistors not working because you don't have a ground path here. Now if this M9 is available here, so M10, it is both these transistors will be switched on out here. So these nodes will be pre-charged to 1. Okay, they'll be pre-charged to 1. Now if you see, this is 2 NAND gates which are cross connected. Right, cross coupled. So we have learnt about SR latch, right? So in SR latch, if you give 1-1 out here, in this particular case, since it is a NAND gate, if you give 1-1, you can't give 0-0 here. If you remember from the previous class, if you give 1-1 here, it will retain the previous value. So the previous value will be retained here. Like for an NOR 1, we can't give a 1-1. If it is a NAND, if 1-1 will indicate that it will slave to the previous value. You can remember that from here, our previous class discussion. So this is for when the clock is low, previous value is retained here. When the clock is going high, right? So this M1 will be switched on. Now if you see, this is a differential amplifier, right? So now what is the advantage of having a differential combination here? Because this will be current starved. So the current available will be available on, so any increase in current in M2 has to result in decrease in current in M3 because this M1 cannot provide adequate current to both these transistors, so it will be current limited here, right? So any increase in M2 will decrease the current in M3. Similarly, any increase in M3 will decrease the current in M3 because the current is limited by M1. So if you have a small differential voltage which is coming here between in and in bar, that is the bit and bit bar line from the memory. So it will amplify that difference out here. And if you see here M7 and M5 and M8 and M6, they are two inverters, and the output of one inverter is converted to the input of the first inverter, and the output of this inverter is connected to the input. So they are cross coupled inverters, right? So the moment the clock is going high, this M1 is switched on, and you have this these two acting like a differential input, and it will these two inverters which are cross coupled, so they will toggle the state to 0 or 1 depending on which is higher. If in is high, then accordingly this will become low and this will become high. So correspondingly, if in bar is high, this will become low and this will become high. So so this is a cross coupled inverter which is driven by a differential amplifier, and accordingly the outputs will be set to high and low. Okay, so that is the how this works. Okay, now the purpose of M4 is during steady state conditions. Okay, you want these two like when it is pre-charged to 1 and 1. Okay, whatever residual voltage out available here. Okay, during state. So this is a weak M4. So these two nodes also will be charged to they'll be equalized, so that this is off here. So you don't want these to be whenever the clock is low, all these have to be in the same potential, so that whenever a clock is going high, so the necessary differential action takes place. So this M4, it is a weak one, so whenever the clock is low, it is switched on, so it is like providing an DC path from here to here. Okay, so it's a DC path where these two node voltages will be made equal when the clock is low. Okay, so that is the purpose of M4. Okay, so this is all theory which we want to cover today. So thanks a lot. So